You can also set up your own parameters. For example, you can see here, I got it commented out because I tried it out, but it didn't work very well. You can set your parameters inside this get transform yourself. For example, you can say, yeah, don't flip it, set the rotation to be nothing, 0, 0, and don't warp it. So you can still override those default parameters. If you want more information about this get transforms, just put a dock in front of it like this and click the run button, and you get this kind of output. And here you can see some of the defaults that are being set. You can click show in docs, and it goes over here, and it loads up this get transform here, so you can read up a little bit more about what it does here. So you can see these different parameters is what they're doing. All right, so that's a little bit about loading all the images. So what we have to do now is we have to load them. So this will take a little while. It's going to load up all those images. It's going to randomly select 64 at a time. It's going to set up a data collection, and then it's going to normalize it based on those image stats. So we'll let that run. And one thing you can try out down here is once this data has been created, you can look at the classes that it's using, and that might be useful to see the position of the classes. Which one comes first? Is it the normal? Is it the ammonia? So here's a little bit of information after the data bunch has been created. It tells you how many items are in the training set. So remember, it's set aside 20% for validation. So now there's a 320 left for training. It tells you a little bit about this image size, 224 by 224 by 3 filters, red, green, blue channels, they call them. And there's 80 images that's going to be used for validation, as you can see here, and it tells you where it's located. So now that we have done the data collection, we can click on this data classes, and you can see normal is showing up here first, and then ammonia. Internally, FastAI keep track of the number of classes that you use, because it goes into the calculations when they create this. Because one thing they will do is they will, in the method that we're going to be using in this video, is called transfer learning. And in transfer learning, you have to peel off the last few layers, and then you have to add how many classes you want the output to be. And it uses this .c to figure out how many classes it needs to create. So that's what that C can be used for. Now we can show some of the images from our data that we collected up here in a image data bunch. So we click that. So it uses this show batch method. I want to see 3 rows, and I set the figure size to be 7 by 8. So once it's done loading those images, they will display them here below this cell inside this Jupyter notebook. And again, if you want some more information about this show batch method, just do a doc in front of it here, and it will take you to the documentation. Okay, so now it's loaded, and here you can see some sample images from that batch, the mini batch of 64 that was created. So it has pneumonia, normal, 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 normal. So these are the type of images we're going to use for our image classification. Now we're going to be loading the model. And again, several of these models come packaged into the FastAI library. For example, the ResNet 50 architecture is in there. There's a ResNet 34. I'm not sure if there's a ResNet 102. I haven't really looked, but I like the ResNet 50. ResNet 34 is probably the one you should play around with first, because it's much smaller and it'd be easier to train. It takes less time. But ResNet 50 seems to be a good model to use, and that's the one we're going to be loading. So in order to load a model, you use this CNN learner, and you can see it has a lot of parameters set up in here. And one of them it requires is the image data set, which we called data, that we loaded up here in this image data bunch. I call it data. We're going to pass that in. The next thing we want is to specify the model here. And the number of models in this case was ResNet 50. And you can see there's some other models listed here too. There is some DenseNet models. There's AlexNet. there's ResNet 101, SqueezeNet. You have the bunch of VGG 16, 19 models here. There's a lot of models. You can see it here. Very, very loaded a lot of models in here. I'll use the ResNet 50. The metrics I want to display both. If the model is already loaded into your Colab, it will simply reuse it. But if not, it will go out there and it will grab the model from this website. And we know it's a Pytorch model because it has the extension PTH. FastAI library is built on the top of Pytorch. We want to make sure we run it on a GPU. So you can use this torch method to set it to CUDA, meaning you're going to run it as a GPU. So that's why we do this piece here. I already ran this, so I'm not going to rerun it in this part. I'll show you again what it will look like when you run it, but let's just kind of read it off for now. The first thing you want to do is use this one cycle approach, which FastAI is using all the time. And the one cycle approach is a very useful approach. Okay, so let me click here. This one cycle approach is basically taking your, it bumps up the learning rate. It keeps increasing the learning rate and plot it and run through an epoch or a complete passover of all the training data. And then it will plot it against the loss it produces. So it keeps running this and bump up the learning rate from very low to very high. And as a result of that, you'll be able to pick a very good learning rate that's going to help the speed and everything and the results from your training. Another thing it does, it determines how much momentum to use to get to this point. So it's a very nice way of getting really good results by running it in much less time. So almost everywhere you see these FastAI, they run this fit one cycle. So now what we want to do is we want to run the learner and we want to fit one cycle. And basically what it does is it peels off the top layer in your model. It removes the classifications from the top layer because this model was trained on something called ImageNet data. And ImageNet data was, I think, is 1.4 million images in 1,000 categories. And we have a binary outcome here. We have either you have normal or pneumonia. We don't need 1,000 classifications. So we need to remove that and add our own classification. So this fit one cycle here, I just set it arbitrarily to be 5 here. It means it's going to run a full iteration over the training sets. It will handle one mini batch at a time, and it will go through a full training of that mini batch. That's what I call an epoch. And we are running 5 epochs, meaning 5 iterations. So let's try to run that and see what it looks like. So as you can see, it produces some progress bars. And you're in the first iteration here, 0 out of 5. It's going to run 5 epochs. And each epoch takes about probably 20 seconds or so. Keep in mind, it puts all 64 images on the GPU and parallel process them for each epoch. So this will take a little while, and I'll let it run, and then I'll pause the video and get back to it when it's done. Now you can see it's on his last epoch. It's 4 out of 5. And the first one was really slow, but after that, it's about 20 seconds. So now it finishes the last epoch. And notice already we're up to 91.25% accuracy, which is pretty good. So what we're going to do next is we simply want to save this model. And you can do that by saying learn, save, and give it a name. Now, I already saved this before, so I want to give it a new name here. And then once you save, you can reload it back again and start using, because whatever is trained to at this point is right here. You can also run a summary. So when you run a summary of your model, it produces a lot of output. Keep in mind, this is a ResNet 50 model, so it's going to have 50 layers in here. And the meaning of these layers we're going to talk about in a different video. I'm going to go through some more stuff, what all this stuff does and how these parameters are computed, etc. But you can see it's pretty deep. And if you look towards the end here, there's a total of 2,161 trainable parameters in this model. So obviously running like at 20 seconds is pretty good, right? Per epoch. Anyways, next we're gonna unfreeze the whole network and we're gonna train it again and try to improve that performance.